Now let us see the second type of differential equations, which is homogeneous differential equations. These equations are of the form dy by dx given by some function f of x and y, where this function is a homogeneous function in x and y. Now by homogeneous function we mean all the terms in the expression of that function are of same degree. So in other words, we can also write the expression of the function as, say, f of x and y equal to lambda raised to n into f of y by x, where lambda here is some arbitrary constant and that exponent n is called as the degree of that homogeneous function. So second degree homogeneous function, for example, means all the terms are of second degree in it. So we can have some expression as given by something like x square plus say xy. Now if some function is given by this particular expression, you can see that there are two terms and each term is a second degree term because x and y are both variables. So that is what is called as a homogeneous function. So in short, the homogeneous differential equation is nothing but the derivative dy by dx is basically some homogeneous function of x and y. And to solve this type of differential equation, we use the substitution y equal to v into x and then solve the differential equation, right? Now let us see some example of this type. Here we are given dy by dx is equal to y plus square root of x square plus y square upon x. Now if you observe the right hand side, y is of first degree, x is also a first degree term. Now inside the square root we have both second degree terms. So therefore, since the square root is taken, ultimately that entire term becomes the first degree term. So therefore we can say that the given differential equation is a homogeneous differential equation, and therefore we substitute y equal to vx. Now see, we have to differentiate both sides with respect to x, so therefore dy by dx gives us, now to differentiate the product of v and x, we use the product rule. So that is first function v into derivative of second function x, which is 1, plus second function x into derivative of first function, that is dv by dx. So therefore in short we have dy by dx as v plus x into dv by dx. So let us use this substitution in the given equation. So therefore we have, now in the given equation we have dy by dx on the left hand side. So let us write it as v plus x dv by dx as we have just obtained is equal to, on the right hand side y will be replaced with vx plus square root of x square plus y square is nothing but v square x square by putting y equal to vx whole upon x as it is. So that gives us vx plus, now if we take x square common inside the square root and take that x square outside the square root, we will have x into bracket square root of 1 plus v square, correct, whole upon x. So that in turn gives us, cancelling x, we have v plus root of 1 plus v square, alright, and on left hand side we have v plus x dv by dx, right. So v gets cancelled from both sides, and now we see that we can bring the term in v on left hand side and the terms in x on right hand side. So therefore we get 1 upon square root of v square plus 1 dv is equal to 1 upon x dx. So therefore on integrating we get, let us integrate here itself. So on integrating, for the left hand side the integral is of the form 1 upon square root of variable square plus constant square. So 1 can be written as 1 square also, and we know that the derivative of the integral of this particular function is given by log of mod of v